Hello and welcome to lecture 21 of the course Computational Complexity. In this lecture, we will see space hierarchy theorem, right? So in lecture 13, we had seen time hierarchy theorem, right? And let me just recap. Time hierarchy theorem basically said that if you have more time, then you can compute certain languages or problems that you could not do if you did not have that more time, right? So having more time certainly helps, right? That is what we could infer from the time hierarchy theorem, right? To be more precise, let me just write once again. To be more precise, it said that if gn log gn was little o of fn, then d time gn is strictly contained in d time fn. Okay, basically if you have more time, then you could compute certain functions or certain languages which you could not compute if you had the less time. So space hierarchy theorem is going to be very similar, just the time is going to be replaced by space, and even the proof technique that we are going to use is going to be very similar. So if you may recall that we had defined time constructible function. Similarly, for the time constructible function, we defined for the time hierarchy theorem. Similarly, we will define a space constructible function. So what is a space constructible function? Basically, it is a function fn such that fn itself can be computed in fn space, right? So the space required to compute the function is equal to the is at most the function itself, right? And a bit more technical detail is that the input should be given as a unary string, as a string of ones, the number of ones being the input n, and the output should be the actual function, right? Because we have to write in unary the input because usually the input length is always n, right? So here we want to write the input in unary, right? So this is the definition of space constructibility. Basically, a function fn should be computable in the space bound given by the function itself. Time constructible was exactly the same, just that you had to replace this space bound with a time bound, right? And like I said, for time constructible functions, most of the familiar functions that we have, like n squared, n log n, square root n, log n, everything, all of this is space constructible. You will have to think of really obscure functions to get something that is not space constructible, right? So maybe one exercise that you can try out, why is log n space constructible? Can you see how to compute, given n or given n ones in a string, how can we compute log n in using at most log n space? Okay, you can try that. So now let me formally state the space hierarchy theorem, right? So for any space constructible function f, right, there is and a function g such that gn is little o of fn, there is a language A that is in D space Fn, sorry, but not in D space Gn. So Fn is a time constructible, space constructible function, and consider a function that is little o of Fn, meaning little o means limit Gn divided by Fn tends to 0 as n goes to infinity, right? So Gn grows at a strictly smaller pace than Fn. Limit Gn divided by Fn goes to 0. In such a case, right, there is always a language that can be decided in Fn space but cannot be decided in lesser space than that, in Gn space, right? So just to formally, or to state it in another way, so if Gn is little o of Fn and Fn is space constructible, then D space of Gn is contained, but strictly contained, in D space of Fn. Right, so this containment is strict. This is what space hierarchy theorem means. So just to contrast this with time hierarchy, it's exactly the same, just that in the time hierarchy theorem we required Gn log Gn to be little o of Fn. Over here we just need Gn to be little o of Fn. So there was a gap of log n that was required in the case of time hierarchy theorem. In the case of space hierarchy theorem, we don't need that. So even things that are very close, closer than log n, but as long as they are little o of Fn, it's fine. So for instance, if, like, let's say Fn is n squared, or let's say Gn is n squared and Fn is, let's say, n squared square root of log n. Even in this case, D space of Gn is strictly contained in D space of Fn. Whereas we cannot use the same G and F for time hierarchy theorem, because this does not have a gap of log n. This G and this F, we need a gap of log n, which is not there for this G and this F. We cannot use these two functions to get a gap in the case of time hierarchy theorem, right? So that is a statement. What is the proof idea? The proof idea is also, idea is also very similar to that of time hierarchy theorem. So I will present it slightly differently, so that maybe sometimes when you see multiple or slightly different way of presenting the same thing, it helps the understanding better, right? So you may recall that in the case of time hierarchy theorem we used diagonalization, right? So we first saw the proof of the halting problem or the acceptance problem, and then we saw how to modify that, how to adapt that for the time hierarchy theorem. So here, since we had only recently recapped that for the time hierarchy theorem, I am not going to recap the proof of the halting problem, but I'll just use the same, but then the techniques are exactly the same. So what did we do in the case of time hierarchy theorem? We basically had a machine that simulates another machine. So if you recall, we wanted to show the separation between n and n squared. So basically we would simulate an n machine with in n squared time, right? Sorry, n power 1.9 time, right? So this is what we had. So whatever input we get, the input being a Turing machine, we just simulate the machine on its own description for n power 1.9 steps, and then reject and flip the output, right? So here, so basically we simulate the machine on its own description and then flip the output, while making sure the time was at most n power 1.9. In the case of, so here we will, one change in the presentation is that here we will stick to abstract functions and not specific functions like that, because we have already seen it. So maybe I would like everybody to be comfortable with this abstract function. So we will not use concrete functions. And second point is that we wanted to show that we wanted to run for n power 1.9 steps, which is something less than n squared but more than n. So here we will try to do the same thing but with space. So we will make sure that it takes adequate space but no more than fn, right? So it runs, so we will try to simulate a gn space machine with an fn space machine, but we will have to curtail the space usage. So that brings in a small difference on how this implementation is done. And again, to answer the earlier question that I myself had asked, in the case of time hierarchy theorem, we have this log n factor, right, this one, which is not appearing in the space hierarchy theorem, right? There is no log n here. Why is that? If you recall, in the time hierarchy theorem, we had used a certain result that to simulate any Turing machine with its description by Henney and Stearns, right? Which said that any Turing machine that runs in time t needs t log t time to simulate by another Turing machine, by a universal Turing machine. But however, in the case of space restricted Turing machines, we can simulate it, and there is no need of this extra log factor. So that extra log factor does not appear in the equivalent simulation of the space bounded machines, and that is this extra log factor that we are saving in the space hierarchy theorem. Okay, so now let us get on to the idea. The main idea is to construct a deterministic Turing machine that simulates all the gn space machines and flips the output, right? And then flips the output. And so, and whatever is a language accepted or recognized by the Turing machine that we construct, that will be the language that is in d space fn but not there in d space gn, right? So basically what we do is we first check whether the machine first checks whether so the input is read as a description of it is interpreted as a description of a Turing machine, right? So you could describe that Turing machine. So is it a description is first checked. This is something that is straightforward. Are there states, are there transitions, and so on. If it is a description, if it is not a description, it is immediately rejected. If it is a description of a Turing machine M, say, okay, if it's a description of M, then what it does is it simulates the machine M on its own description, right? So if it is a description of a Turing machine, so then D simulates the machine M, so on the description of M, right? So this is the description of the Turing machine M, right? So this is used to, this M with angular brackets is used to denote the description of the Turing machine M. So it simulates M on an input, so the input could be anything. So here we are simulating it on its own description and then flip the output, right? And there are some things that can happen. One is that the machine may not halt, right? How do we deal with that, right? And second is that it may take more than the allotted space, right? So we want D to be an Fn space bounded machine. So these two things have to be prevented, right? It not halting and it taking more space. In the case of time hierarchy theorem, we stopped the simulation at a certain point, right? Because we wanted the time to be bounded. But here it's not a time bounded machine. So how long do you keep simulating? So this doesn't halt problem. How do we stop it, right? So we'll address both. So what we'll do is so the question is, how do we check these two, right? This and this. So one is, so one meaning this one doesn't halting, not halting. So we will use, we will use a counter based time limit, and for 2 basically we want to constrain the space usage, right? So we will just mark some cells as unbounded, like as you cannot, as out of bounds, right? So mark the tape cells as out of bounds. So basically we say which is the territory that the machine can operate. And there is another, so these two handles, these two solutions handle these two issues. The another thing is that this was also there in the case of time hierarchy, but perhaps I didn't elaborate to this detail so as to not cause any confusion, because I wanted to make it essentially the diagonalization. So now that we have seen diagonalization, I just want to bring out this particular issue. So one is that even though Fn is or Gn is little o of Fn, right? It could so happen that for small values Gn could be higher, right? So what I am saying is, so the graph could be something like this. So this could be, maybe the red is Fn and Gn could not like this, but maybe something like this. Let's say this is Gn, green is Gn. But for small values, so in this case, it is possible that Gn is little o of Fn, right? So maybe what I have drawn looked like a constant, but maybe there is this needs to taper off slightly, okay, something. But the point here is that in this region, right, in this region, Gn is greater than Fn, right? So in this shaded region. So, but that's okay, because all that the asymptotic says that if Gn is little of Fn, at beyond a point this should happen. Gn should be less than some constant times Fn for any constant, right? So we will choose. So we will choose, or we'll make sure that the n that we have, we have to make sure that the n that we have is beyond this place. It is sufficiently large. Maybe the n that we have is restricted to this point or something, beyond this big, beyond this rightmost line, because there has to be sufficient gap between Fn and Gn. So we'll choose the n such that it is sufficiently far away to the right, where the asymptotic effect has happened. So these are the three issues, and these are how they are addressed. So now let us see the description of the Turing machine, or more formal description of the Turing machine, right? Of the machine D, whose the language that is in D space Fn is the language recognized by D space Fn, but not in D space Gn, right? So what is D? So given an input W, okay, you measure W, measure the length of W. So length of W is, let's say it's n, and compute Fn. Okay, so you compute Fn, and this is why we need Fn to be space constructible, because we want to mark out Fn space. So for that we need to know what is Fn. So for that we need to compute Fn, but then we only have Fn space. That's why we need Fn to be space constructible. So we mark Fn space in the tape, and if the simulation at any point crosses this Fn, so you put a marker or something, if it crosses that marker, you immediately reject. So anything that you compute, this computation will not cross that marker, okay. That is step 1. And now you look at the input. So if the input is not of the form, the description of a Turing machine, followed by 1 1 and a string of zeros. So this is 0 star. 0 star means it could be 0 0 0 0 0 0 something. If it is not of the form, this form, a description of a Turing machine, 1 1 and a bunch of zeros, you reject. So it has to be a description of a Turing machine, 1 1 and a bunch of zeros. So the bunch of zeros could be 0 0 or 1 0 or many zeros, more than 1 zeros, right? Now you simulate the machine M. Okay, so there is a description of a Turing machine. M stands for the description of a Turing machine. So the same M, you simulate the machine M on W. So W is M followed, description of M followed by 1 and the many zeros. And see, and while keeping track of how many steps you make. If the number of steps exceeds 2 power fn, right, we reject. Why do we do that? This is because we want to be more than any GN space bounded machine. So any GN space bounded machine will have 2 power constant GN number of configurations, and therefore that many number of steps. So while 2 power fn is bigger than GN, sufficiently bigger than GN. So 2 power fn will be sufficiently bigger than 2 power c, constant times GN. That's why we stop the number of steps at 2 power fn. Okay, so otherwise how will we know if it continues running, right? So if the count exceeds this, you reject. Now what you do finally is to flip the output. So this is just flipping of the output. If M accepts, then you reject, and if M rejects, then you accept. Okay, so now this may seem a bit cryptic, but all that we are having, so which is slightly different from the time hierarchy theorem proof, is that we have this description of M followed by 1 and a bunch of zeros. So and then M is simulated. In time hierarchy theorem we simulated M on its own description, but here we are simulating M on the input string, which is the description followed by some bunch of 1 and zeros. So this 1 and zeros, the role it plays is to make the length sufficiently large so that we are in this rightmost region, right? That is the role that it plays, right? And then we flip the output. And step 3 is making sure that it doesn't run too many steps, right? So anything that runs in GN space can be decided in GN space will not take more than 2 power fn steps. Okay. Now what is the language that is in D space fn but not in D space GN? It is the language of this machine A. Now clearly what is the space usage of D, right? In order to simulate, so first one point is that M is being simulated by D. So we may require, so the alphabet of M has to be written in terms of the alphabet of D. It may or may not be the same. So that brings in a constant overhead, right? Constant overhead. So C times the space usage of M may happen. So this is, and this is the main overhead. If M uses GN space, D will use constant times GN space, where the constant is denoted by the letter C. And in the case of time hierarchy theorem, right, we had a log overhead for the simulation, whereas in the space hierarchy theorem, the overhead is just a constant. And then this is what I said earlier, we want to make sure that we only consider large enough n. So what we do for that, we will choose an n where, so this constant C, right, C times Gn is less than Fn. So we will choose a constant, or we will choose n such that C times Gn is less than Fn for all the n above this value. So we will choose all the n to be above n0 where n0 is this cutoff point, where Gn is, or C times Gn is Gn is sufficiently smaller than Fn, or C times Gn is also still less than Fn, and it continues to maintain this continued to maintain beyond that point, and there will be such an Fn because Gn is lid low of Fn. So This is to make sure that the asymptotic effect has kicked in. Okay, so that takes care of the details. And now let us see what happens, the final contradiction, right? So what happens now when the machine D is fed a machine M, the description of a machine M, followed by 0, 1 and 1 repeated n0 times, right? Now in this case what will so now D is not, M is any machine, okay? So M is a description of a machine, so the first step will pass, right? This will pass, and the length is n0 plus 1 plus the description of M, and it will mark sufficient space, right? The space required for this will be Fn, and Fn we know that it is more than n0, right? So n is at least n0, so we have at least n0 once. So f of n will be at least c times g of n. So M has enough space to successfully simulate, D has enough space to successfully simulate M. So D can simulate M and then flip the output, right? So D, when it is fed M, description of M 0, 1 power n0 will be opposite of whatever M does on its own description, or M does on this same input, M description of M followed by 0 followed by 1 power n0. Okay, this is because D has the time and space to successfully simulate M, because the space bound and the time limit is chosen such that the input length is chosen such that the space bound and time limit are respected. Now A cannot be decided in lit law of Fn space, right? This is the contradiction. Why is this? Suppose M is a decider for, suppose of course D takes order Fn space. Now suppose there was another decider M that uses lit law of Fn space. Let's say it uses Gn space. Let's say M is a decider for A that uses Gn space. But we already said that now what happens when D is fed description of M followed by 0 followed by 1 power n0. Description of M followed by 0 followed by 1 power n0 is fed to D. So what we just saw is that D will do whatever, the opposite of whatever M does on this. Okay. So but then now M is supposed to be a decider for the same language as D. But then we just saw that D will do whatever, the opposite of whatever M does. This is a contradiction. So M and D disagree on this input, right? So that is a contradiction. So M cannot be a decider for the same language as D, which means D has to be which means there is the language decided by D, which let's call it A, cannot be decided in lit law of Fn space. So we get the statement of the space hierarchy theorem that D space Gn is strictly contained in D space Fn. Strictly means it is subset but not equal to D space of Fn whenever Gn is a lit law of Fn. Once again, why is it called hierarchy theorem? Because it defines a hierarchy in the space usage. For instance, right? So let's say Fn is Gn is n and Fn is n squared, then we get that D space of n is strictly contained in D space of n squared. And let's say maybe D space of log n, what is this? This is nothing but L, is strictly contained in D space of, I don't know, okay, or maybe why not P space. In fact L is actually contained in, it's even contained in D space of n itself, right? So D space of n is contained in P space. So you could say this as well. So basically there are, for any two functions f and g, if g is asymptotically smaller than f, then there is something that is decided in f space but not in g space. Just a short quick recap of the main idea of the diagonalization. The language that is decided in f space but not decidable in g space is not explicitly defined, but through the construction of a Turing machine, right? So by construction, this Turing machine uses at most fn space, right? So basically it marks off fn space, and then it has a counter that goes up to 2 power fn, but both of them use fn space. And then what it does is, what we make sure is that the input is of sufficiently long length so that the asymptotics have kicked in, so that any input of length gn can be simulated in this space, right? And so we first see that any Turing machine of length that uses gn space, when you feed its own input to this machine, so when you feed the input m1 followed by n0 zeros to d does the opposite of whatever m itself is supposed to do on the same string, right? Suppose this is w, so what d does on w is the opposite of what m does on w, because d is programmed to do that, right? Because d simulates m on this and then does the opposite, right? And right, so now what if m decides the same language as d using lesser space than d? Then by the same argument, d disagrees with m on this input, which means m cannot be deciding the same language as d, and that is a contradiction. So we assume that there is a machine m that decides d using lesser space. That assumption was incorrect, and that summarizes the proof of space hierarchy theorem. So just like we had time hierarchy theorem, we also have space hierarchy theorem, right? So you can do more things if you have more space that you could not have done if you did not have the extra space. Okay, thank you.